future is next year or next moment. AI will transform the education from knowledge feeding to people development to adapt to the quickly development of the world. University should be redefined. XJTLU is trying very hard to reflect what's the future education and reshape the learning and the teaching.
The world is no longer a little oyster. Everything is international. We are combining the holistic approach to education of the East with a more analytical approach of the West.
After joining XJTLU and studying with teachers and classmates worldwide, my world expanded. I gained a more diverse perspective and many new ideas.
Before coming to XJTLU, I was already very excited about China's ancient culture. To my surprise though, when I came here, I was also able to witness a lot of advanced technology.
The future society is an ecological society oriented by science and technology. We invite students to think of ways to best integrate and collaborate with AI and robots and strengthen the most human parts in the system.
XJTLU is intended to broaden students' research horizon across disciplinaries.
When we put all the expertise together, this helps the students to work as a group and come up with better solutions.
Many students will worry about the future, but here in XJTLU, we welcome you to the real industry.
Because in future, the boundary between university and society will disappear.
Our faculty, they are internationally renowned researchers. They truly care for our students.
We always appreciate their ideas. Even some crazy idea, you never know, it might happen. This is how the Nobel Prize has been given, because it might become a real.
Through our collaboration with XJTLU, we have improved our industry ecosystem. We can share cutting-edge research findings with students. The students can also infuse our projects with innovative thinking.
Our professors don't force-feed knowledge to us. Instead, they guide and support us in realizing our dreams based on our needs. They make learning experience so fun and provide us extra information about our future career paths that I really, really love.
XJTLU taught me critical thinking and lifelong learning. Through the learning mode, I could acquire new skills and interacting with teachers and alumni every year after graduation.
The students and the professors are always growing together as a community. We're constantly learning from them, improving and adapting our offerings.
You can feel that this university is alive. It's a constantly integrating, self-involving platform, enabling them to act, feel, and think about themselves in new ways. This process always empowers our students.
Certainly in the future, we would face a lot of challenges. Do your best to make a contribution to the future. You would find more opportunities, more colorful, exciting future journey. We would have more competitive global citizen, which will help us to develop a better world for the future. That's my passion. Future is next year or next moment. AI will transform the education from knowledge feeding to people development to adapt to the quickly development of the world. University should be redefined. XJTLU is trying very hard to reflect what's the future education and reshape the learning and the teaching.
The world is no longer a little oyster. Everything is international. We are combining the holistic approach to education of the East with a more analytical approach of the West.
After joining XJTLU and studying with teachers and classmates worldwide, my world expanded. I gained a more diverse perspective and many new ideas.
Before coming to XJTLU, I was already very excited about China's ancient culture. To my surprise though, when I came here, I was also able to witness a lot of advanced technology.
The future society is an ecological society oriented by science and technology. We invite students to think of ways to best integrate and collaborate with AI and robots and strengthen the most human parts in the system.
XJTLU is intended to broaden students' research horizon across disciplinaries.
When we put all the expertise together, this helps the students to work as a group and come up with the better solutions.
Many students will worry about the future, but here in SJTLU, we welcome you to the real industry.
Because in future, the boundary between university and society will disappear.
Our faculty, they are internationally renowned researchers. They truly care for our students.
We always appreciate their ideas. Even some crazy idea, you never know, it might happen. This is how the Nobel Prize has been given, because it might become a real.
Through our collaboration with XJTLU, we have improved our industry ecosystem. We can share cutting-edge research findings with students. The students can also infuse our projects with innovative thinking.
Our professors don't force-feed knowledge to us. Instead, they guide and support us in realizing our dreams based on our needs. They make learning experience so fun and provide us extra information about our future career paths that I really, really love.
XJTLU taught me critical thinking and lifelong learning. Through the learning mode, I could acquire new skills and interacting with teachers and alumni every year after graduation.
The students and the professors are always growing together as a community. We're constantly
Good evening, dear students, colleagues, and audiences online. Welcome to Professors of XJTLU Public Lecture. 欢迎各位莅临在西普听讲座。I'm Professor Beibei Tang from the School of Humanities and Social Sciences. It's my great honor to be the academic chair of this lecture series. The Professors of XJTLU Public Lecture is our university's signature event for scholarly communication and knowledge dissemination. At XJTLU, we now have nearly 80 professors, and we would like to promote our unique research culture through them. This public lecture series will be presented by XJTLU professors from various research fields, showcasing their career-long research, a thorough review of selected research topics, and the latest developments in the field. The lecture series will be offered throughout the academic year to XJTLU staff and students and the public. Through stimulating presentations using plain language, the professors of the XJTLU Public Lecture Series will explain complex research topics and showcase our university's research impact and contribution to our community and society. Today's speaker is Professor Jin-Tai Ding. Professor Ding is currently the Dean of School of Mathematics and Physics at XJTLU and a Charles Phelps Taft Distinguished Professor Emeritus at the University of Cincinnati. Professor Ding received his PhD from Yale University in 1995. Before joining XJTLU, he was a full professor at Tsinghua University. Professor Ding is one of the designers of the only quantum-resistant key establishment standard by the US National Institute of Standards and Technology. He is also the inventor and patent owner of the first quantum key exchange, which was one of the 2 patents licensed to NIST for ML-KM. Professor Ding is currently working on quantum cryptography. He and his colleagues developed the Rainbow Signature, which was the 3rd round candidate and the finalist in the NIST post-quantum standardization process. He and his colleagues also won the Best Paper Honorable Mention Award for Crypto 2021. Professor Ding served as co-chair for the 2nd, 10th, and 11th International Conference on Post-Quantum Cryptography. In March 2025, Professor Ding's team achieved a milestone on the fundamental breakthrough in a security analysis of lattice cryptography. Today, we have the great honor. In this lecture, Professor Ding will introduce post-quantum cryptography and its recent development. We will let Professor Ding give the lecture first, and then we will open the floor for questions and discussions. So without further ado, I give you Professor Jingtai Ding.
Okay, thank you. Thank you very much. Okay. First, of course, I would like to thank the organizer for giving me the opportunity to talk here. And actually, I will do it in a slightly different way. I already said it earlier. So if you have any question, or the online audience as well, feel free to interrupt me. So therefore, we don't have the format that I give a lecture at the end, ask questions. So if you have any question, feel free to ask me. So I came more or less, I think I came from the US. In general, I have an idea about lecture, meaning when I go to lecture, I spend 1 hour there. If I don't understand anything, I'll be very upset because I waste all my time. So therefore, I will do my best, try to make it as accessible as possible about this talk, okay? So let me start now. So the title of the talk is Post-Quantum Cryptography, a New Era. So therefore, my main job is to explain to you what is post-quantum cryptography, its development, and so on. I will make it as accessible as possible, I think. Okay, let's start. So in order to talk about post-quantum cryptography, which is I call it modern cryptography, I should first introduce what is called traditional cryptography. Okay, so let's start. So what's the difference? The difference is that modern cryptography is what is called asymmetric, and traditional cryptography is called symmetric cryptography. So let me start with a very simple example. And this is the first cipher ever invented by human beings, and this is called the Caesar cipher. Okay? And I use English as an example to explain how it works. It's actually very simple. You have 26 letters. You make 2 loops. Each loop has all the letters in order. Okay? And then you rotate the loop inside. After you rotate, for example, in this case, I rotate the inside the circle counterclockwise 4 positions. And then you can see there's correspondence from letters from inside to outside. Okay? So once you have this, you have an encryption method, which means I have an original message which is called plain text. So what is plain text? Plain text is something you can read, like a newspaper. Encryption, I would like to change to something you cannot read. So what do we do? It's very simple. What you do is you have a plain text, which is readable, and then you change the letter according to this loop, which means you have a plain text. When you see A, you substitute by E. You see B, substitute by F. Okay? That's it. This is called the encryption process. Okay? And decryption process, when you receive a message, encrypted message, what do? You go the other way around. It's as simple as that. This is invented by Caesar. Okay? Yeah? So here, in order to decrypt properly, we must know how many positions rotated. So we have to use exactly the same position. So therefore, the sender and receiver have exactly the same information. Therefore, it is symmetric. Or in Chinese, it's called 对称. Okay, traditional cryptography. Okay? And this is the Caesar. We know. He's the king of Rome. Okay? And then I would like to give you an example of what he would do. For example, he doesn't really like the Gauls. He would give an order, say, let's attack the Gauls. Suppose he and his commander agreed on the cipher I just described. Instead, he will not send this. What he will send is this. This is the encrypted message. Okay? If you look at the attack, A becomes E. Agree? And then when the general receives the message, the general will go the other way around, recover the what? The original text. So this is it. This is the famous Caesar cipher. Very easy to understand. But here, the most important property is symmetric. The sender and receiver must have exactly the same information. Okay? So the mathematics behind it is very simple. You realize what we're doing is what? We create a map from 26 letters to 26 letters. But this map has to be what is called a bijective, meaning you can go map it one way, but you have to be able to go back. That's all. Okay? And let's see security analysis. It's very interesting. Okay? And you realize, hey, this is not secure at all. Do you agree? Because there's only 26 possibilities. Therefore, I can easily guess one by one. Agree? But we can easily improve it, which means I do not arrange letters in order. Instead, I do a random permutation, which means A. For A, I choose randomly a letter, and then B, I choose a random letter, and still I create a bijective map. Therefore, the choices will be 26 factorial. And if you want to do brute force attack, which means you want to try one by one, it's impossible. Agree? But it's still not secure. Okay? And I will introduce the first attack in cryptography is called a chosen ciphertext attack. Okay, we know. So when Caesar sent the order out, his messenger could be kidnapped, could be killed, could be captured by the enemy. And they were the intercepted ciphertext, which means he will receive what? What is called what? Encrypted message. Agree? It can be easily lost. Because the message is on the way, right? You cannot protect message all the way. But if you use English, English has a very interesting character, which means English letters has what is called a proper distribution in some way. For example, if I intercept enough messages, I can figure out which letter is E. Can someone tell me why? Because in English, letter E appears with the highest frequency, which means once I intercept enough message, I just count the frequency. I know which letter is E. Which one? Which is the letter has the highest what? Appearance, frequency. Okay, can someone tell me what's the second letter? Come on, you should know. Huh? No. No. It's letter T. Yeah, so this is it, okay? And then you can say, oh, this really doesn't work, right, in English, right? But then we can improve. You realize what we did is on one letter. I can do on two letters, do you agree? But then the length starts to go longer, do you agree? So two letters have 26 square elements, and you can make a table. One-way encryption, one-way decryption. But still it's not good enough, which means you can go to three letters. But the table gets longer and longer, it gets what? Less and less what? Efficient. But it's getting more secure. Agree? Okay, then let's jump to the modern time. Sorry, just a second. I want to add something. So this is a mathematical talk, so therefore I want to talk about mathematics. Okay, so today I want to go home, learn some mathematical concept called the modulus. Okay, so I wanted to learn something about modulus. Okay, so what is a modulus? For example, if n equals 26, I want to define mod n. Mod n, which means given any integer, I will divide by 26. I only care about remainders. Is it clear? Remainders. So therefore, if you divide by 26, what are the remainders? Remainders are what? 0, 1, 2, 3, all the way to 25. Those are possible 25 classes. Okay, for example, 28 is the same as 2, because 28 is equal to 1 times 26 plus 2. The remainder is 2. Okay, this is the first definition. Modulus, remainder. Is it clear? But the most important thing interesting is in mathematics, you can do operations. For example, I can do additions. For example, 13 plus 14 equal to what? Equal to 1, because 13 plus 14 equal to 27, 27 equal to 1 modulo 26. Not only we can do addition, we can also do what? Multiplications. Same. Okay, 7 times 8 equal to 56. 56 equal to what? Equal to 4, because the 56 equal to what? 52 plus 4, 52 equal to 2 times 26. So the modulus is 4. So you can do operations. Yes? Maybe I'm asking, what is 121? 11 times 11. What is it equal to? Can someone tell me? 100. No, 11 times 11. Remainder. 121. What's the remainder? Mod 26, yes. 18 or 17. Okay, so 121, right? Let's look at 26 times 4 equal to what? 104. And then 121 minus 104? 17. So he's right. Okay, let's do a simple one. 29 times 14 equal to what? Can someone tell me? This looks very complicated, right? Because you should remember 29 equal to what? Equal to 3. Agree? 3 times 17 equal to what? 51. 51 equal to minus 1. Minus 1 equal to 25. So equal to 25. Mod 26. Okay? And then why do I do that? The reason is once you define modular, we can define functions such that can represent the encryption. For example, we can do something called encoding, which means when Caesar sends a message in some 26 letters, Caesar can just send a 0, 1, 2, 3, all the way to 25. Do you agree? Right? 0 is A, 1 is B, and therefore the Caesar cipher is what I describe is fx equal to x plus 4. That's the encryption function now. And then the inverse is fx equal to what? X minus 4 is a decryption. That's it. To realize encryption decryption can be what? Expressed in mathematical formulas. And here the most important thing is modulus. We don't treat it as real numbers, we treat it as modulus. This is a human invention, okay? Yes? And one example, actually, think about 5. 5 actually is invertible in multiplication. So if I define function fx equal gx equal to 5 times x, modulo 26, what's the inverse? Inverse is 21 times 6. Why? Because 5 times 21 equal to what? 105. 105 equal to 104 plus 1. Agree? Therefore equal to 1. So there are 5 and 21, they are inverse to each other, but are multiplicative inverse. Okay? So you should realize, when you define modulus, when you define encoding like what I described, what you're doing is actually doing mathematics on those modulus. Okay, this is, remember, I will use it again, modulus. Okay, this is what it is. Okay, then once we realize that you cannot do by hand, what do humans do? We replace by machine. Do you agree? So the most famous machine in terms of encryption is the Enigma machine used by Germans in the Second World War. I think you all heard about stories. Okay, Enigma machine mostly used in the German U-boat, which is submarine. Okay, this is what? A machine of it. And if you look at this machine, okay, look very carefully. You look at these things, those are the routers. The keys are decided by those router positions. You can see in spirit, we are doing the same thing as what? As a Caesar cipher, in spirit. Okay, so this is an Enigma machine. Okay, and the later American did DES, called the Digital Encryption System, and then the AES, Advanced Encryption Standards. So this is what American did later. But again, those are what? Symmetric encryption, which means in order to use Enigma machine, the sender receiver must have exactly same what? Keys. Is it clear? Okay, so which means when you do sending, when you do receiving, you put those routers at the exactly same position as the keys. Then you can encrypt, and then you can decrypt properly. So which means you have to agree beforehand. So which means on each U-boat, they would have what is called a key book. And they are exactly the same book. And then before I start, I will say, today I'm going to use page 5, number 5. Only if you have a key book, you know what is on page 5, number 5. Otherwise, you have no nothing. So therefore, the most important thing is to protect the key book. Otherwise, you are dead. Okay? Okay, so this is it. And one thing very interesting, okay? So since this is not a very, I don't want to be too technical, then one thing you should challenge yourself. You read all the historical stories, you suddenly realize only the submarine use this. Why not? Other things, for example, German army do not use it. Why? Can someone tell me why? So there were about 400 submarines. Okay? So which means each submarine, before they leave the port, they have to go to headquarters, get what? A key book. Okay, they have to protect the key book with their life, because once this key book is gone, the whole navy's all the operations are known to the enemies. But submarine has one very good property, which is when you are attacked, what happens? You sank to the bottom of the ocean. So therefore, your key book what? Is protected. But if you give it to army, for example, each battalion have one book, and number one, there are so many of them. Number two, normally when you're defeated, there's a high chance this book will be what? Will be captured by the enemy. Then you're dead. So therefore what? Therefore such an operation is not scalable. They only use for small number of people, so you can ensure the key book is protected. So embassy use it, government use it, but not in a wide scale. So this is a very important. Okay? So later, when you look at these things, so this is mathematics. So what we do here, the routers using mathematics, which means they are doing what is called a composition of simple functions to produce what? Complicated functions. So I will skip over here, okay? And I still skip over here. But I would like to emphasize the DES, the first global international encryption standard, used two very simple functions. Number one is map S, x1, x2 to x2, x1. Number two is you map tx1, x2 to x1, and x2 plus fx1. F is any function x1. And the inverse, just subtract. It's unbelievably simple. But they have to go through several rounds of what? Iteration, composition iteration. Okay? That's too complicated. I will not go to more. But let's look at history again. So we know the German Enigma machine was broken by what? By Turing. But the first thing was not done by Turing. The first actually is the Polish people. For example, this name, you should remember Marian Rejewski in 1939. You would ask me, why the Polish are interested in breaking German codes? It's because after the First World War, the area of Gdansk was given to Poland. And Gdansk separated East Prussia from West Prussia. So they have to talk to each other. So they put the listening station in the middle, so they start to study German Enigma machine. And that's what happened. And in the end, they told the information to Turing, and Turing helped to break it. Okay? So for me, there's a very interesting story here concerning Turing. Even though Turing is the guy who designed the machine to break it, actually the machine was made in actually what is called Dayton, Ohio, by a company called the NCR, National Cash Register. So they make cash register. I think we all know. So in Chinese it's called 收银机, so which means when you pay, there's a machine there, you can type. Okay, they actually built the machine. Okay, but for me, the funny story I want to tell you is that after the war is over, the US Navy went to the NCR, said, let's work together, build computers. The NCR said, no, we are not interested. We'll keep making NCR. NCR does not exist anymore. Imagine if NCR agreed to build computers, Silicon Valley will not be in Stanford, will be in Ohio Valley, in Dayton, Ohio. So this is a history, is very random, very strange, okay? And then one more interesting thing is, we all had the impression that only the Americans doing code breaking and so on. It's not true. Japanese actually did a very good job to attack US Army code. They were so good that the American force do something extraordinary, which is called Navajo talkers. I don't know if anyone heard of it. Do you know what it is? So let me repeat. US Army code was broken by Japanese for a lot. So they are very worried. So instead what they do is they hired a bunch of Navajo Indians. You know Navajo Indians? So this is one tribe in the United States. Okay, they will send one Navajo to each battalion. So when the boss gave an order, he will talk in English, and the Navajo talker will what? Understand English and speak over openly to the other Navajo on the other side. The Navajo understood it, and then what? Translate into English to the what? To the other battalion commanders. Unbelievable, isn't it? So yeah, this is a human what? This is a human encoding machine. Okay? If you're interested in history, you can look at it. Okay? But what I really want to talk about is Turing's story. So we know Turing died in 1970s, right? 70s. He was homosexual, he was caught, and he was punished, and in the end he killed himself. Why didn't the British government come out to save him? Why? Turns out that the British government kept the fact that they broke the Enigma machine secret until 1980s, 1990s. Can you tell me why? Because after the war, many countries still use the Enigma machine, which means the British government knew everything you talk about on the radio wave. For me, the most extraordinary story I heard is in 2019, I went to Brazil, give a talk. And there's a guy invited me, his name is Tareda, Professor Tareda. He's a Brazilian Japanese. Yeah, he told me a story. That's extraordinary. I think Professor Fu probably knows the Falkland Island War. Or do you know Falkland Island War? No, this is the island off the coast of Argentina, belonged to Britain. And then Argentina took it, and there was a war during the Thatcher time. They sent the Navy to what? To take it back. And this is called the Falkland Island War. Do you know what the Argentine Navy used during the time? Enigma machine. So basically the war is over before it started, because the British knew everything the Argentine Navy was doing. Because the Argentine Navy did not know it was broken. So this is I tell a story with a purpose, okay? So this is about this is Navajo talkers, okay? This is a picture about it. If you want to read about it, this is you can find it. So this is Alan Turing, okay? This is we all know. So what's the conclusion? The conclusion is that symmetric key is actually very good, more or less. It's very difficult to break it. Even though Turing break it was not easy, very costly process. But the most important property you should learn is this thing is not scalable. That's the most important. But it was okay, right? It was used by Navy in submarines. It was used by government in embassy. It was fine, no problem. Okay, but the conclusion is not scalable. So what is the problem? The problem is in 1960s, 70s, we started to build what is called computer network. So we have many, many devices. Now we have billions of devices, and we all want to talk to each other securely. Now it is a problem. For example, in China, we have 1.4 billion people, right? If I want to talk to 1.4 billion people, I have to meet every one of them to key exchange. What's the consequence? The consequence is this: I will do nothing in my life. The only thing I do is what? Do key exchange. That's not acceptable. Okay? So we must find new solutions. So this is a jump from symmetric cryptography to asymmetric cryptography. And this idea was first proposed by Diffie-Hellman. They won Turing Prize in 2016. This is Diffie and Hellman. Okay? And this is the guy who did it, which means Diffie-Hellman proposed this idea, but their mathematics is not good enough. They could not do it. But there are the three guys who are, this from the left to right, Reverse, Shamir, Edelman. Reverse computer science, Shamir computer science Edelman number theorist. Okay, I know Shamir very well. He explained me the story. I think I should explain to you. Okay, so there's also some guy else involved. His name is Andrew Yao. In Chinese, Yao Qizhi. He's a professor in Tsinghua. He's also a Turing Prize winner. So the history is amazing if you think about it. So this is what Shamir told me in person. So Shamir got his PhD from Weizmann Institute. Okay, he didn't have a job, and suddenly he got a job. Why? Because somebody in MIT quit his job, and this guy's name is Andrew Yao. So he went to MIT. Okay, he went to MIT, and his next door office, who is next door? Revest. They were both Jewish. They like each other. They say we should do something together, but they don't know what to do. Okay, one day, Shamir went to the library of MIT, and he found a book. He found a paper left on the table. Do you know what that paper is? That's the paper written by Diffie Hellman. Talk about this new idea. And we don't know who did that. And Shamir took this paper, and went to Revest, say we should do it together. They decided to work on it. But they couldn't do it. And they have a next door neighbor is Edelman, who's a number theorist. Three of them work together. Start to try to solve the problem. They tried many, many things, failed. And then there was a Passover dinner, and Revest, it's actually Revest got drunk. And 6 o'clock in the morning, he called them, say, I got it. This is the world-famous RSA crypto system. I'll try to explain to you a little bit. Okay, so therefore, from my perspective, especially for young people, I want to tell you scientific research is not just about hard work. Luck is also very important. You never know. Okay, but Shamir actually told me Shamir, he told me even more amazing story. So when he did it, he did not know how important it was. So they published a paper, but at that time, they published what is called extended abstract. It's very short. At the end of the paper, that time there's no internet, 1970s. At the end of the paper, he wrote one sentence is, if you're interested in the full version of the paper, please write to me. And he left for summer vacation. And when he come back for summer vacation, the secretary gave the keys to him, look at him in a very strange way. He didn't know why. And he opened the door, there were hundreds of letters asking for the full paper. And then he said, I realized, he said to me, okay, at that time he realized he did some good work. Amazing story, isn't it? Yes. Okay. So this is the three guys. Okay. So this is yeah. So what is the mathematics behind it? Mathematics behind it is very simple, because in the design of ISA crypto system is based on what is called integer factorization. So now today, so I said I will do an interactive lecture. So I want all of you take out your cell phone. Can you please get your calculator? Okay, so can you calculate 7433 times 9857 on your calculator? You get it immediately, do you agree? And do another one. 102953 times 99317. Calculate it for me. Very easy, right? Immediately, right? Okay, now I'm going to trouble you, okay? And then my next question, can you factor this number? I know this number is a product of 2 prime numbers. Can you do it? So this is the principle of ISA. The asymmetrical properties. What does it mean? It means that given two large prime numbers, it is easy to multiply them and get a number. Your calculator can do it. Doesn't matter how large. We can do it immediately. But if you give the product, ask you for the factor, it is very, very hard. This is the asymmetrical property coming from. Okay? So is it clear? So this concept is what ISA is. They use this fact to design what is called the first public key cryptography in ever human history, RSA encryption scheme. So now, instead of having symmetric keys, which means sender receiver have exactly the same, we have two keys, essentially. One is N, which is public. I'll tell everybody. And you can use it to what? To send me information only I, who knows the factors, P and Q, can decrypt. And you realize this is a very important solution, because this is what we call the one-to-many. Because on the network, I can announce to the whole world on my website, my N. After that, anyone can what? Send me a message, only I can read it. Because only I know PQ, which is the private key. That's the basic idea. This is the design of ISA. Okay? So, yeah, so it was proposed by 1970. The idea of public key cryptography was proposed by David Hellman, but the people who did it is, they proposed the idea asymmetrically, okay? And then they did it is ISA. So ISA, so I will simplify it. Just forget about it. The most important thing to remember is it's easy what? Multiply two numbers. It's difficult to what? To factor it. So therefore, the public key is the product of two prime numbers. And what? The private key is the factor. So the security relies on how hard it is to factor it. That's it. Okay, so this is ISA. Okay, I don't want to go over, okay? But once this is published, we realize there's even more important in network security, which is called authentication. So in China, when you go to train station, right, you always hear the new, what they're saying is, right, if somebody calls you, says your uncle needs money, this is what? This is a fraud, right? And blah, blah, blah. What's the problem? The problem is on the network, when you receive a message, most of the time you don't know who sent it to you. Do you agree? You need something called authentication, which means we have to have a mechanism such that when I receive a message from my father, I know it's not from my father, it's not somebody else who pretends to be my father. It turns out the public key created the same thing, which means we can use the public cryptography to design what is called digital signature. I think this invention is even more important than encryption. Okay? Well, I'll explain to you a little bit why. But in this case, the same design. So which means whatever I do is I have my public key, which is N again. Okay? And now I have what? The factor PQ. I can use PQ to sign a document and attach to my document. And anybody with N can verify it's from me or not. Is it clear? The signature. So it never happened in human history, right? I go to bank, I sign some document, so nobody knows who I signed, if I signed it, right? Only the expert. Maybe even experts don't know. But now it's completely different. Okay? So this is a digital signature. Okay? The most important thing is the public key is verified, private key use the sign. And this is how we build what is authentication. Okay? So now in the network, so let me talk about practical use. Okay? In the network, how do we use it? First, key exchange or asymmetric key exchange. It's always used to encrypt the keys. We never use the encrypted information. Why? Because public key cryptography is very slow compared to symmetric cryptography. So for those kids, young kids who play computer games, we cannot use the public key to do what? Computer game, because the speed we cannot catch. So therefore, we only use what? Let me repeat. We use the public key cryptography, only send the keys. Then we switch to what? Symmetric cryptography. Okay, this is number one. Okay, and number two. Number two is, for example, I give an example, right? We all use Windows system, right? In Windows system, one thing we'll do often is what? Do system updates, right? Can someone tell me what do we do when we do update? Check the line. How? No. How do you know? How do you know if somebody changed it? So you receive a new package, right? Software package. How do you know if somebody changed it? How do you know it's not from Microsoft? The reason is Microsoft, for example, for Windows, Microsoft announced to the whole world this public key. Okay, we all download it from Microsoft. When I receive a software package, I can use it to verify it's from Microsoft. If anybody change it, if I do anything, then what? Then I know. So this is for authentication. So in these days, authentication is much more. Okay? So what does that mean? It means one of the audience, any of you, if you can factor this number, you can, in the name of Microsoft, send a software package to update. Even if it's a virus, all our computers will run it automatically. You can imagine how much power you have now. So we are living in a very interesting era. Okay, this is a update. Okay, I will say that in the God of math we trust, because this digital signature. So in China we use it for legal documents, we use it for deeds, we use it for insurance. Okay, and we use it for logging to your bank account. So what does it mean? That means if one of you have the power to affect the number, you are more powerful than the president of China, you're more powerful than the president of the United States. Even they cannot do that. So therefore, we live in either we trust math as a god. Okay? So this is where we are now. Okay? And now let's talk about quantum. Why do you talk about quantum, right? You have a quantum. So next thing is we'll talk about, I wanted to tell a little bit something more interesting, Bitcoin. Okay, well, I don't want to tell about the value. I want to tell you the design. So Bitcoin is called a cryptocurrency. Does anyone know how it works? Digital signature. So in cryptocurrency, in the case of Bitcoin, they're just numbers. Okay? So how do you decide the ownership? The ownership is attached to the public key. So which means what? 50 Bitcoins attached to this public key, 55 attached to this public key, we have a list there. But how do you use it? So suppose I have 55 Bitcoins, I want to give some to her. She has a public key too. What I do is I write a transaction, say, I agree to give her 5 Bitcoins and the 50 to return to me, and then I sign it. Because my public key is attached to it, therefore I can use everybody can use my public key, verify it is I who agreed to give her 5 Bitcoins. Once that is done, and that's it done. Okay? So therefore what? Therefore Bitcoin is nothing but what? But a string of numbers describe the transaction and signed by the legitimate user. That's it. It has no other value. And here, maybe I should emphasize, there's no encryption. Okay, no encryption. Only what? Digital signature. And there's another thing, I don't have enough time. I will jump over it. It says use something called a hash function to do POW, proof of work. I will skip it, okay? So this is I will speak. And then let's jump to cryptography again. So it turns out Diffie-Hellman did something even also interesting related to key exchange. This I want to tell you a little bit. This is also related to what is called the Snowden story. Okay? So how does ISA work? ISA works is I have a large number n. Anybody can use n to encryption, and then only I can decrypt it. Therefore, we can build a shared keys. Like Professor Fu, for example, I have an n. Professor Fu download my n and send me what? A secret key, encrypted key. Then I decrypt it. Afterwards, we can talk. But Diffie-Hellman proposed something actually even simpler. But why is this important? This is related to what is called a forward security, and which I will not talk about either, but let me describe Diffie-Hellman. Diffie-Hellman is the simplest, most elegant mathematical application I ever found out. Okay, I explain to you very simple. So he didn't want to do key exchange. So now modulus is very important. Okay, everything is mod p. I already defined modulus, right? You agree, right? So I will use that now. Okay, so we'll choose a large prime number p. All the calculations are done modulo p. Clear? Then Diffie and Alice and Bob, two guys want to talk to each other. They want to build a shared key. What Alice will do is secretly choose A, and Alice will compute g to the 8th power mod p. Bob will secretly choose B, not showing anybody B, will compute g to the bth power. And then they openly exchange. So what you could see is g to the A, g to the B. When Alice receives g to the B, Alice will compute g to the B to the 8th power. And Bob will compute g to the A to the bth power because Bob has B. But they are equal, right? Because they are equal to g to the A times B. So therefore, they build what is called shared keys. Okay? But what is the mathematics behind it? Mathematics behind turns out there's a very hard mathematics called discrete logarithm. Remember, I know g to the 8th power. If you don't do modulo p, it's very easy to compute A. But once you do modulo p, this is what is called a discrete logarithm. And it's very difficult to do. This is another way to do it. Interesting, isn't it? Okay? So this is called discrete logarithm. So what is the conclusion? The conclusion, at this moment, our whole world is built on these two algorithms. One is integer factorization, another one is discrete log. If you can solve this problem, you're more powerful than Trump. You're more powerful than President of China. Because you can go to any bank, change the numbers. Nobody knows. This is where we are now. Isn't it unbelievable? Yes? This is unbelievable, yeah? You control the whole world if you can do that. Okay, this is where we are now. Now let's talk about quantum, okay? So does anyone know this picture? Anyone see this picture? It was very popular a few months ago. This is a picture showed on the newspaper of the Willow superquantum computer by Google. I think you've seen it before. When I said that, you saw this picture before. So what? No, this is from Google. This is from Google, okay? So now I want to talk about quantum computing. So what is quantum computing? The idea of quantum computer was proposed by several people. One of them is Richard Feynman. This is a very famous physicist who won the Nobel Prize. Okay, and this is a picture showing him on the hearing about the Challenger accident. Okay, he explained very easily why Challenger collapsed, exploded, not collapsed, exploded, because the seal was what? Was brittle when the temperature is low. So he's very famous. So what is the idea of quantum computing? He asked the following question: is it possible we can use the quantum mechanics principle to do computation? He wants to do that. Let me repeat. Okay, instead of using physical logic circuit, he asked, can we use the quantum mechanics principle to do computation? And this is called quantum computing. Let me repeat. The definition of quantum computing is we would like to use a quantum mechanics principle to do new computing. This is the definition. But when he proposed the idea, the same in the 1970s, 80s, we do not know what to do with it. Nobody studied it. Nobody cared, because there's no way we can show at the time it's doing better than traditional computer. No. Okay? And then somebody else showed up. So this guy is Peter Shor. Okay, in 1994-95, he suddenly invented a new algorithm called Shor's algorithm. What does this algorithm do? This algorithm can solve discrete logarithm and the integer factorization very fast on a quantum computer. Theoretically. What does it mean? What Peter Shor said is that if you have a large quantum computer, using his algorithm, he can very efficiently factor. He can very efficiently solve discrete log. Which means if you have a quantum computer, use a Shor algorithm, you can conquer the whole world. But at that time, we don't have any quantum computer. Nobody cares. 1995. And for me, something different happened. In year 2000, I saw news. Last year, I got a tenure in University of Cincinnati. I got a tenure, and I want to do something different. Because I was doing algebra, I was bored. I want to do something different. Then I saw this news. This guy, his name is Isaac Chuan. He's now a professor at MIT, just like Peter Shor. Peter Shor is also a professor at MIT now. So he did something amazing. Okay, and also very funny in some way. He spent $15 million to factor 15 equal to 3 times 5. We know, anybody can factor 15, right? Any elementary school student can factor 15. But the difference is that he built a 7-qubit quantum computer and performed Shor's algorithm and factor 15 equal to 3 times 5. This is called a proof of concept. So to me, he proved that if you can build it, we actually can run the algorithm. So at that time, I decided I would like to do something different, which is what I called what? Post-quantum cryptography. So what I realized is that once people build a quantum computer, you need what? New replacement for the existing system. And this new replacement is called post-quantum cryptography. What is it? It's a new public key cryptography or public key crypto system that can resist quantum computer attacks. That's the definition. This is called post-quantum cryptography. This is what I did. So I gave up everything I did at that time. In year 2000, I started working in this area. I never studied with cryptography before, but I was tenured, so I don't care. That's a good thing about US tenure system, yeah? If you look at my Google citation, you realize that my citation like this, and then go down. You realize I was doing something else, and I started climbing up again. So this is what happened, okay? And then for us, the fundamental change happens in 2015. August 19, 2015. So out of the blue, the US government, this is the NSA, suddenly announced, okay, they suddenly published in their webpage. The most important thing you should read is here. This is August 2015. Say, IAD will initiate a transition to quantum-resistant algorithm in not too distant future. What does it mean? It means the NSA decided United States government will replace the existing public key cryptography with post-quantum cryptography. That's it. That's what it is, 2015, okay? The US is very interesting, okay? Even though NSA announced they would do it, but in US, the security standard, especially crypto standard, is done by somebody else from the Commerce Department. It's called NIST, National Institute of Standard Technology. Okay? So they decided, okay? They have a post-quantum crypto group, and they decide to make a standard, okay? And they immediately take actions. For example, they say, this is disallowed. They start to take actions. Okay, this is what they do. Okay, this is still acceptable, this is disallowed, and so on. So they start to take action. Okay, and then they announce. Okay, this is exactly what I said. The NIST said we need to make a new standard for these two categories. Number one, key exchange. Number two, what? Digital signature. Okay, so this is what they announced. Okay, turns out that in the post-quantum cryptography we have these mainly five families of systems. One is called the code-based crypto system. This is used error correcting theory. And then hash-based signature is used hash function. And the isogeny cryptosystem uses isogeny of elliptic curves, and the lattice cryptosystem uses lattice to do, and the multivariate using polynomials. I mostly work on numbers 4 and the number 5, lattice and the multivariate. This is what I do, okay? So let me tell you a little bit of my journey, right? Since I would like to talk about my work, and then, so when I start to work on this, and I had two choices, either do ISA or the Diffie-Hellman. So I decided to choose what? Diffie-Hellman, okay? I chose Diffie-Hellman. Then I'm a mathematician, right? So I would like to think in abstract ways. I would like to understand why Diffie-Hellman works. And if you look at it, then I immediately get the conclusion. Diffie-Hellman works because of the following mathematical phenomenon. You have a function fx equal to x to the 8th power. You have another function hx equal to x to the bth power. And then the fundamental reason they work is because fx composed by gx equal to gx composed by fx. What does it mean? It means these two functions commute, and the composition, not the multiplication, okay? Composition of functions. Okay? And I look at it, I thought this is easy. I should be able to do it. Just find something commute. Okay? But there's also one more interesting phenomenon happened, okay? So you have ISA, and then you have what? Diffie-Hellman. Diffie-Hellman directly do key exchange. After ISA is encryption. Turns out there are many new inventions of crypto systems to use encryption, but Diffie-Hellman, no replacement. We could not find anything new. For example, people use braid groups to do it, they all failed, they all broken, okay? And then I had a student, PhD student, we decided to work together. For 5 years, we could not do anything. I spent 5 years work on it. Okay? In the 5th year, I found a paper and they completely defeated me. So in the 5th year, I found a paper written by this guy called Joseph Ritt. Okay? And this paper was published in 1923. Okay? So what did he do? He wrote a paper to prove the following result. If you have two rational functions, permute, and the composition on the complex plane, there are only 3 choices. Number 1, power polynomial, x to the a, x to the b. Number 2, Chebyshev polynomial. Number 3, rational function come in elliptic curve. Turns out that all these things are very similar. They all belong to what is called discrete log problem. They all can be defeated by quantum computer. But he said you have no other choice. So I decided to give up. So I was doing something else. Okay? So that's it. It's totally broken. This is Joseph Ritt. If you're interested, and this is a paper called The Permutable Rational Function, Joseph Ritt, 1923. He was a professor in Columbia University. Okay, I spent 2 or 3 months understood the paper, but now I forgot everything. It was not easy, okay? If you're interested, you should read it. This is a fundamental paper, okay? And then I was with my wife. We were in Germany as a Humboldt fellow. And then in Germany in 2006, I was there and started to hear a new idea called the learning with error. And then I realized I had a chance. Okay? I will simply explain how it works, okay? So learning with error idea is very simple. You try to, given a system, you try to add a noise. That's the basic idea. Okay? And then we know in mathematics, it's a very interesting phenomenon, which means when you have 3 matrices multiplied together, you multiply from left or multiply from right, they what? They commute. Because it doesn't matter you multiply 2 first. This is the associative law. So therefore, you realize that multiply left and multiply right, they commute. Doesn't matter who does it first. And then I realized I had the opportunity to do something new. So I want to use this, okay? So I will not go over the technical details, but I would like to emphasize this thing very much. So at the moment, okay, the NIST standard mostly are built on this LWE. Okay? Idea is about add noise. It turns out this idea was actually invented far ago. This is related to history. I like history very much. So at the beginning, I told you, right? Diffie-Hellman first invented the public cryptography idea, and the ISA first realized it. But turns out later we found it's not true. 10 years before Diffie-Hellman, there's somebody called James Ellis. He actually invented the same idea inside the GCHQ, which is the British NSA, but he's not allowed to publish it. He proposed exactly the same idea, public cryptography. But he did not invent ISA either. Okay? But where does this idea come from? Turns out his idea coming from a paper written in 1945. In 1945, during the war, the British and Americans collaborated extensively with each other. Okay, they share all the papers. And the one paper invents something more or less like LWE. I can explain to you very easily. So when I do communication, for example, if I want to talk to Professor Fu, what I would do is I would build a channel, and then I would actively add noise over the channel. And then Professor Fu will talk over this channel, because I am the person who adds the noise. So therefore, I know how to what? Denoise it. Other people cannot denoise it. This is the idea. This idea inspired James Ellis to invent this public cryptography idea, but he was not allowed to publish, and we knew it later. And then later, there's people, so if you want it, you can check Wikipedia, and later there are two more people who invented Diffie-Hellman and ISA independently. One is Clifford Cox, he invented ISA. Another one is Malcolm Williamson, he invented Diffie-Hellman. Separated in 1973. Again, they were not allowed to publish. Very bad. Nothing you can do. So we still call Diffie-Hellman. We still call ISA. Okay, so this is what happened. Okay, history is very important. This is James Ellis. He already passed away. Okay, and then now I want to today, as this is the only slight mathematical work I would like to do. I would like to introduce what is called learning with error problem. Okay, and then ignore what I wrote here. You just look at the matrix. Okay, you look at the matrix. Suppose I'm a physics professor. I teach your class doing experiments. Suppose those B's are measurement. Okay, this AIJs are parameters. It could be temperature, it could be pressure, and so on. I know the measurement, they have linear relations. So which means I know B should equal to A times S. S decides the linear relation. But we all know when you do experiments, especially you have too much beer the night before, when you measure, your hands will shake a little bit. So what happens? What happens is that you would have error terms. Do you agree? And if you're not too drunk, the error should follow Gaussian distribution. Do you agree? Which means most of the time the error should be small. Maybe from time to time you have one, a little bit further down. So what is learning with the error problem? Learning with error is very interesting. This is a problem not over real numbers, it's over ZQ. Modular. So this is really related to discrete logarithm. Logarithm problem is very easy to solve, but discrete log is very hard. The same thing here. So this problem, if it's continuous, we know how it's very easy to solve. This is called the least square method. We can solve it easily. But once it becomes ZQ, it's very difficult. And then you will say, how do you define the error? The defined error is related to what is called discrete Gaussian, which means, remember ZQ, right? Would choose, I showed you already, right? For 26, the representative are 0 all the way to 25. But for ZQ, if Q is a prime number, we don't do that. We choose a representative from minus Q minus 1 over 2 to Q minus 1 over 2. And then the distribution is given by Gaussian like that, which means still most of the time we'll give 1 minus 1, 0. Sometimes we'll go off a little bit. So what is it? This is a discrete linear algebra problem with noises. Turns out this problem is very hard. Okay? So I'll jump over it, and then I would like to say what I did is I used this problem to build a new key exchange. And I don't want to go over details, okay? And what's the difference I did? The difference I did, I don't want to go all the mathematics already. The difference I did is I realized the following phenomenon, which means you should realize when you do LW Diffie-Hellman, afterwards the two sides result will be different, but by a small error. Okay, but we have to reconcile in the end. So what I invented is a reconciliation algorithm related to this phenomenon. What does it mean? So when you have two results very close, if your error is small, if your results are on the upper half, if your error jump and jump, there's no additional modular involved. Therefore, I can easily get the same value. But if you are near the boundary, one error could jump this way, one error could jump other way, then there will be one more modulus operation. Therefore, the result will be not matched. So I found a way to deal with this problem. The way I found it is I did what is called signal function. So Diffie-Hellman, you look at Diffie-Hellman is G to the A, G to the B, then done. We just go our ways. But here, no. Because my 5 years painful experience, I realized you cannot do it directly. You have to do one more step, which means you have something called a signal function. Once you have a signal function, it can help you to reconcile, to build, share the keys. This was my invention. So I invent first post-quantum key exchange like a Diffie-Hellman. That's it. Very simple idea. But you should realize it took me 10 years. I started 2000, and 2005 I gave up, and then 2006, 2007 I picked up, and then 2010, 11 I finished. 10 years. Okay? So this is what I did. Yeah? And then this is mathematics. Let's skip over it. Okay? So there's also very interesting story involved this. Okay? What time is now? Sorry, I have to look. So very good. I'm very much on time. Okay? So I invented, then I published a paper in 2012. There's another guy called Chris Pikert. He rewrote my paper and claimed he invented. And what's the difference? The left-hand side is my signal function. He changed a little bit into this one. He claimed he's first ever invented. So people actually believed her first. They call it a packet key exchange. But one good thing I did is I filed a patent. Okay? So this is very important. Okay? I will forget about it. Okay? So I'll skip over it too. Now let's talk about NIST. So NIST has a call for standard in 2016, deadline in 2017. They say we'll choose next generation standard, and the three criteria is security, cost, algorithm, and implementation characteristics. So which means what? You have to be secure, you have to be fast, and easy to implement. That's all. Okay? And then in 2023, they select 3 algorithms to be standardized, 4 algorithms to be standardized. The main algorithms are Kyber and dilithium. Kyber is key exchange, dilithium is for signature. And my name is on the Kyber. The reason is because I have a patent. So I licensed my patent to NIST. And I mean, that's why I could get it. At the beginning, my name was not on it. Okay, this is the result of negotiation, okay? The alternative are Falcon and Phoenix Plus. Kyber, dilithium, Falcon, they're all lattice-based schemes. Okay? Okay, and then we'll go for the next, okay? And this is what NIST gave to me as for recognize my contribution, so outstanding contribution. This is for the Kyber case, and they give me this thing. And then this Kyber is already made into the standard called the FIPS 203, and it's done this year, last year, August 2024. This is the only, at the moment, this is the only key exchange standard post-quantum. FIPS 203. Okay, if you're interested, you can find a document. Okay, and then one more thing interesting I would like to describe you. Okay, they made a standard. You notice, right? We choose one word, key exchange. We have 3 signatures, but NIST is still unhappy. NIST say we need more signatures. So they have a new round call for signatures. Okay, the deadline was June 1st, 2023, and there were 50 submissions. Okay, I submitted 3 of them, and 2 of them made it into second round. Okay, and the most interesting phenomenon is that after 2 days, many of them are broken already. So it's not easy, what I would emphasize. Okay? So then I would like to talk a little bit about mathematics, lattice. Maybe you heard me, lattice. What is a lattice? Lattice is just a grid, what? In the vector space. Okay? Those dots represent the vectors. Okay? Lattice has a property, any 2 dots add together, still inside. Any dots multiplied by what? Integer, still there. And given lattice, you have what is called a basis. For example, this B1, B2 is a basis, which means that any vector can be written as an integer linear combination of B1, B2. So what is the design principle of a lattice? Is I give you a random basis whose vectors are very long. Your job is what? Find a short vector, especially the shortest. This is called the SVP problem. This is the NP-hard problem. Our security relies on this problem. Okay, before is factorization. Now is what? SVP. That's the difference. And the quantum computer is not yet shown to be effective on what? On solving this problem. Okay? I'll skip over this. And what I will emphasize is, how do we know how secure a system is? Turns out we have to do real work. For example, in 2013, my friend Johannes Buchmann, who is a professor at TU Darmstadt, he set up a challenge called a lattice challenge, which means he creates problems at different dimensions. If you can solve it, he will put your name there, you are the world champion. Okay? And this represents the best performance we could have openly. Yeah? And what happened is that in March this year, with a student of mine, Ziyue Zhao from Tsinghua, we actually solved the hardest one of all the challenges, dimension 200. Okay? So this is what happened. And if you look at this, is all the past record, and we are here. Okay? And you will ask me, what is the importance, relatively speaking, to current security analysis? So I could solve 200. And if you solve 400, you can defeat United States government standard. That's how far we are. But the problem is extremely simple. You just do random integer combinations, try to find a short vector. That's all. That's all. But as dimension grow bigger and bigger, it's harder, harder, and harder. Exponential growth in general. This is a security analysis, okay? So now I talk about migration. So United States already made the standards, right? What we would like to do is to replace all the existing ISA Diffie-Hellman type of algorithm with the new what? Standards. And this is called a migration, okay? And as I said, it's a great challenge and it's a great business opportunity, okay? And the United States government decided, Okay, so this is called NSM-10, National Security Memorandum 10. This is done during the Biden administration. They decided by 2035, United States government, federal government, will replace all the existing ones with a new standard. Remember, we have to remember we have to look at every cell phone, every computer, every IoT device, have to go inside, take it out, replace it by a new one. So this is what we have to do. The G7 also announced it. Also in the US, the IMF, International Monetary Fund, said they will do it. The Department of Homeland Security will do it. So this is a big problem. Okay, so in the United States, NIST, inside NIST, there's another organization called the NCCOE, National Cyber Security Center of Excellence. They are leading the efforts to do what? This is migration. It's way complicated than we think. I think you guys still remember Y2K problem, right? This is just a fix one bit. Here, what's totally different. It's a much bigger challenge than we realize. So this is the plan of the United States. Okay, so by 2030, this is what we have done here. By 2035, everything has to be done. Okay, so this is it. Now I want to do a summary what we discussed. So you realize, at least in the US, in Europe, they decided that they're going to change everything. Okay, so therefore, we must what? Change every single devices, including cars. For now, these days, cars talk to each other. Everything has to be replaced. Okay, and these days, I would like to emphasize one more thing, which is privacy. Okay, and you should realize cryptography is used everywhere. Okay, I mentioned Snowden earlier. Let me tell the story since I have a little bit more time. Anyway, the Snowden story is also very interesting. Okay, so we all heard the Snowden story, right? What is the biggest secret about Snowden disclosed? Snowden disclosed the following facts. This is related called the store first and decrypt later attack. So if you're interested in the Snowden story, you should watch this movie called Citizen 4. This movie describes the whole story of Snowden. Okay, if you look at the movie, at the beginning, there's a scene of many buildings in the desert of Arizona. You know what this place is? This is a place where US federal government store all the communications on the internet. Let me repeat. They store all the communications on the internet. Why? Because if you use RSA to do encryption, okay, I don't have your private key now. If I have it later, then I can go back to the decryption wall. This is called store first, decrypt later attack. So if you want a long-term security, you must change now. Okay? And the most important thing in cryptography actually is normally two things. Actually, one thing very important is balance between efficiency and security. Normally, more efficient, less secure. More secure, less efficient. And we have to make a proper judgment to choose which class. And this is the most difficult thing. And for Bitcoin, everybody asks me, is Bitcoin okay? No, Bitcoin must upgrade. Okay? So this is more or less what I would like to talk. And then in the end, allow me to do advertisement. So I will build a new lab in PQCX. Anybody wants a job? Apply. Okay, so that's it. That's the end of my talk. And thank you very much, okay? Thank you, thank you.
Thank you very much, Professor Ding, for your lecture. Now we would like to open the floor for questions and discussions. For the audience online, if there is any question you would like to discuss with Professor Ding, please type your question in the chat box and we will get that for you. So if there is any question, you just let me know.
Yeah, please, feel free. You have any questions? Yeah, ask. Oh, I can give him the speaker then. Yeah.
So for the news you shared from Google, how many qubits does it have now?
Not exactly true. We don't really know.
Like more than 1,000 or less than?
I don't know exactly.
Ah, okay.
Yeah, what they did mostly improvements on error correction.
Ah, okay.
Yeah,
okay, so
error correction.
Previously, I saw the news from the IBM one. So they can support like hundreds of qubits at that time. But that's a smaller machine.
No, you have to be very careful. It's logical qubits or physical qubits.
Oh, okay.
They're very different.
Mm-hmm.
Yeah.
Okay.
So for now, I don't know.
Okay.
But you asked a very good question. Maybe I ask you a question instead. Suppose you have a quantum computer where you tell me.
So sorry, could you
Suppose
repeat?
you have a very powerful quantum computer where you where you announce to the whole world, where you tell me.
Oh, no.
Oh, thank you.
No.
You understand, right?
Yeah, okay.
So the reason, so this is very good you asked this question. This is related to why I tell about Turing. You look at Turing's story, you realize that really, if you are a country, if you have a quantum computer, the first thing you would do is keep it secret.
Sure.
And use it at the right moment. Agree?
Yeah.
You definitely will not tell anybody.
Yeah, good answer. Thank you.
You know what I mean, right? So therefore, this is a very important. So actually, people often ask me this question. Maybe I should explain. People always ask me, hey, when will quantum computer come out? I do not know. I'm a mathematician. I follow the progress of quantum computing, but I have no idea. But so actually, in China, there was a debate quite a while already. So whether we should, in China, should do post-quantum cryptography. So my answer is very simple. You don't have to do it. But this is a bet. Okay, you bet the fate of a country on your belief there will be a quantum computer or not. Depends on how you bet. You could bet there will never be a quantum computer. It's okay. Maybe you're right. Are you willing to do it? Do you have the responsibility to do it?
I can't.
Oh, you can't. That's good. But actually, I think China is actually moving quickly these days to try to catch up. Yeah, so there will be a call for standards soon, from what I know. But the US, Europe, Japan, Korea, they're all moving ahead very fast. So this is related to what I described called a store first and decrypt later attack. So if you have any information you want to keep it for long-term secure, you have to do it now. Okay, let me warn these young people. You have an email, very bad email, you delete it. No, you did not delete it. There's a copy in the US government. It could come back to bite you. You should understand that. Yeah. So therefore, it's very important. So we just had a conference on March 31st and June 1. And this guy from AWS, his name is Matt Companion. He's the chief cryptographer for AWS. So this is what AWS is. AWS already moved. So when you use AWS service, now you already can do post-quantum, which means they already can protect you from future attacks. So this is very important. Yeah, okay.
Thank you. Any other questions?
No, Okay, yes.
丁教授可以用中文吗？
Yeah. You say in Chinese, I translate.
那个我代表我朋友问一个问题
好 ，OK。
就是彩虹算法和 EOV 的那个多变量签名，
对，
万一被破解，那么我们如何在那个区块链上，快速敏捷升级到新的那个抗量子算法
？OK。
谢谢。
Let me translate his problem. So there's rainbow system I designed. There's also UOV. He said if we use it for blockchain, suppose it's broken, how do we fastly change it? So this is a very good question, okay? Rainbow, it was attacked, but it was not a fundamental attack, which means you can adjust the parameter easily, and you can fix it. And the UOV never had any serious attack. But if you look at the cryptography, and you should realize we used to think cryptography is forever. We use this system forever, but we are changing our mind. So therefore, at the moment, NIST is promoting very much called crypto agility, which means when we upgrade, not only we'll upgrade in the form such that next time we have to change, we can do it very quickly. This is called agility. We can replace immediately with a new algorithm. Okay? If you look at the work we did on lattice, it's possible lattice has to be replaced too. Because this is a game between what? People building, one is a shield, one is a spare, right? You have a spare and a shield. We are all moving along. You build a better spare, I build a better shield, Mao and Dun. So therefore, in our conference on the 1st of June, and this lady, his name is Lily Chen from NIST. She came to give a talk. The title of her talk is Crypto Agility. The NIST is leading the effort such that to ensure our next generation crypto algorithms are agile, meaning when something bad happens, we can immediately, just like that, not like now. So why do I say that? Because currently there are many systems they are binding together. For example, they build a chip. Chip. One section is cryptography algorithm, and this is terrible because you cannot cut it out and replace it. You have to replace the whole damn system, and this should not be allowed in the future. We would like to take the crypto algorithm out by a mobile module, which means when we realize it's wrong, we can immediately replace it. So therefore, NIST emphasizes very much this concept called agility. So this should apply to what? To what you described, using Rainbow or UOV and so on. We should always keep agile. Meaning when we design it, we should make sure it can be easily replaced. And then we can what? Replace whenever we need. So that would be the suggestion. Okay, let me repeat. Cryptography is just like building a bridge. Nobody promise to build a bridge stands forever. The bridge has a lifespan. The same in cryptography. So I think that's my answer. Yeah, thank you. Yeah, thank you. Okay, Professor Fu, yes.
That is a very interesting lecture.
Thank you.
I just have a funny question.
Yeah.
So encryption gives you a more secure situation, right?
Yes.
So the more complicated the encryption gave you powerful security. Do you foresee any at one point that the encryption is so complicated that we don't even have enough power to solve it?
I don't think so. From what I understand, for example, in particular, look at the symmetric cryptography. Really, we managed to step ahead of time anyway. For now, maybe it could happen, but from the way we see it, no. For example, so we have ISA, we have what? ECC, the curve. Now you can see we have isogeny, we have code-based, we have lattice-based, we have what? Multivariate. We actually have many choices. But the difficult problem, as I explained to you already, unfortunately, not like before. Before, you just have one choice, like ISA. ISA is very interesting. ISA, as long as you increase size of P and Q, you are more secure. But LWE lattice is not like that. We have several dimensional parameters. You have to choose very carefully to make it secure. So we actually have more options now. But from the industry perspective, more options may not be a good idea because the company do not necessarily know which one to choose. This thing's very interesting. No, of course, for research, it's a good thing. We always have a job to do. But on the other hand, I have to assure you that I think overall, so this is the thing I would like to assure you is, this is very interesting. Okay, the point is, maybe I should go back to my talk again. You see, if you look at the modular operation, this is crazy. This is all human invention, do you agree? It does not exist in reality. We invent something in our mind. And turns out it can apply for cryptography. I mean, this ISA is really amazing, right? This PQ thing. So there's a very famous mathematician called, what is his name? Yes, British, Cambridge, what is his name? Littlewood, I think. No. Shit, I forgot his name. He was a number theorist. He's very proud that he studied number theory because number theory is useless. He would be very upset now. We use what? We use prime numbers, we use what? ISA, and can you imagine at any moment prime numbers and the factorization can be used for cryptography? So we are doing, so this ISA thing is really amazing, this ISA thing, right? Just N equal to P times Q. This is a very simple idea. I will go back, okay? If you look at this ISA thing, right? This is just simple fact, mathematical fact, 15 equals 3 times 5. So this is also tells me something interesting, which is mathematical research. Okay? I think it's very important to support abstract math research. You never know what is useful, what is not. And we are making progress, right? Before it was ISA, ECC. Now we actually have more choices. Isogeny, code-based, and so on. But we have to do work on it. Okay? We always will have breakdown. For me, really, it's the same as building a bridge, as I explained. Right? No bridge stays forever. If you have this mentality, then I think it should be okay. So we keep improving. I mean, in most industries like that, especially security industry, right? 道高一尺，魔高一丈, right? We try to what? We try to go one step ahead. That's all. But nobody can guarantee anything. We don't. Okay? Because of the time constraint, for example, I skipped already so-called prover security. We developed something called a prover security. So it's related to achieve the goal. Okay, sorry, I have to flip a little bit. On the prover security, I skip over it. So maybe I should go over quickly what is prover security. So in terms of prover security, we never prove it's secure. Instead, we prove what? Instead, we prove that if you can solve a system, you can defeat system, you can solve a very hard mathematical problem. So we develop a theory like that. Okay, it's a very profound theory, but they're more psychologically useful. They're not practically useful. So once we choose the parameters, you will talk about practical security. The theory does not apply. Okay, so that's why we are doing the implementation, testing things, and so on. Yeah, okay, please.
Professor Ding, I have a question from the audience online.
Yes, please.
Quantum computers are not built yet, but some quantum methods have been broken. How can we have more faith in the new method?
So it's very good. So this is, for example, I will partially answer the question. For example, prover security is a good idea. Probability tells me asymptotically secure, which means even if you break this parameter, I can make it bigger, it's what? Secure. So nevertheless, it's not, how do I say it? It's not a guarantee, okay? So you should realize, same thing applied to medicine, okay? So we had a wrong concept, which means we used to believe cryptography you invented forever. It's same as medicine, right? For example, my joke is that the US Medical Association used to suggest only eat one egg a day at most. Now you can eat as many you want, right? We change our position all the time. We what? This is a science. We move ahead. We do our best. That's all. Yes. And on the other hand, I have to say we are really making progress in terms of understanding the mathematical strategy behind, and we made tremendous progress in the last few years. Yeah, this is the only way to assure. Yeah, we are, but I would like to say we are never 100% sure. Just like when you go out the door, you could be run over by a car, but still you go outside.
Thank you.
Mm-hmm.
Any other questions, comments?
Yeah.
Hello, Professor. I'm a student major in financial mathematics, and I've listened to your lecture on the January of 2024, which is last year. And my question is that because I major in financial mathematics, and recently there's a new emerging industry called quantum finance. So I think that what is the correlations between the post-quantum cryptography and the quantum finance?
I think quantum finance is bullshit.
Bullshit?
Yes. That's all. My answer is the following. Very simple. So quantum computer is for sure to be effective in defeat crypto systems. All the other claims are not yet proven to be correct. They are doing speculations. No, to me it's nonsense for now. Because, for example, I give a very simple example. Okay, this is a very simple example. So he was used to be in MIT. He's now in Texas, Austin. I think it's Scott Aronson. He's one of the leading experts in quantum computing. Okay, and then he moved to Texas, and at that time there's a few people published some paper claim they have a quantum algorithm solve something very efficiently, and then there's an undergrad name. Her name is Amy Tan, I believe. I think it's Amy Tan. I believe Tan, T-A-N Tan. Okay, and her job is to prove that there's no classical algorithm doing better than quantum. But instead, she proved that there exists a classical algorithm run much faster than those quantum algorithms. So in quantum computing, often what they do is very strange. They find very strange problems which nobody cares. And they try to show it's much faster than classical. Why it's faster? Because we don't care. We don't study those problems. Therefore, you do quantum computing much faster. Not because they're really faster. For example, there was this claims called a quantum supremacy. Okay, they claim, so quantum supremacy is a very important problem. Let me define quantum supremacy for you first. So quantum supremacy is we would like to find a very hard problem such that a quantum computer can do better than what? Classical computer. RSA is a good example, but we don't have yet. We don't have no, okay? But then in physics, they what? They have those called the quantum sampling problems. And they claim doing much faster and faster. This is all bullshit. Why? Because they use quantum to simulate quantum. Of course you're faster. They are not solving generic mathematical problem. That's why. Okay, there are many, so we have many disputes. So I'm on the side. I believe it's possible that you will do the quantum finance. But by now, nobody can give me an example in finance that they can do better. That's why I say it's bullshit. So this is all, at least, this here is not speculation. Over there, what? In my opinion, it's speculation. But like what I did before, they could be right, but by now, with my knowledge, I haven't seen that happen. For example, I also studied quantum algorithm. Okay, there's a new quantum, so we have a Shor's algorithm, very famous. There's another one called Grover's algorithm. And about a few years ago, somebody invented called the HHL algorithm. What does HHL do? What does HHL do? HHL solve a huge, sparse linear system very efficiently. But its complexity depends on what is called the condition number. And they claimed it to solve very hard mathematical cryptography. And I proved that no, you cannot. Because they assume the condition number is small. But instead, we prove condition number is very large. Therefore, the algorithm is totally useless. So there are lots of what? In quantum computing, there are lots of what I call speculations. So they have not been able to convince me, at least at the moment, They do better in any other area except factor numbers, except self-discrete log. This I'm convinced. The others I do not know. At least I have not seen any evidence they can do better. This is what I know. So therefore, all the quantum finance, in my opinion, is bullshit. Because they haven't found one single example they can demonstrate that it does it. That's all. Yeah. Okay, thank you.
Any further questions or comments?
Okay.
If no further questions, let's thank Professor Ding for this fascinating talk. To everyone, especially to the audience online, I would like to remind you that Professor Ding's team is hiring right now.
Yes.
So,
yes.
This lecture is the last lecture of this semester's series. So thank you everyone for staying with us. We look forward to seeing you in the new semester. Have a great summer, everyone. Thank you.
Okay, thank you. Thank you very much. Thank you. Thank you.